Maddie, bags, please. All right. Last time, what we learned was how to draw these dot diagrams. And maybe you remember, maybe you don't. Either way, I'm going to review it with you again. But the fact is, any way that you draw it is probably going to be wrong because these are not two-dimensional particles. They are three-dimensional. So the last thing we have to learn in this chapter is how to make them into three-dimensional things. Okay? And the model that we're going to be using is called the VSEPR model, or the VSEPR model.
Let's start with water, because all the interesting things on our planet start with water. It's also universally common, not just on our planet, but in our galaxy and our universe. Case in point, in 2011, astronomers discovered a cloud of water ice surrounding a black hole that contains 140 trillion times more water than we have here on Earth. And while we don't have any confirmed worlds covered in water outside of our solar system, we do have some right here in our solar system. Europa contains so much water, probably salt water, that its entire surface is just ice. What did any of that have to do with atomic orbitals? Nothing. I just felt like maybe I scared you with all that quantum mechanics talk before the intro, and I wanted to chill you out for a second. Okay, so water. We did its Lewis structure last week, remember? Each hydrogen bonding to the oxygen atom and voila. But that drawing is linear, just a straight line through all the nuclei, and we know just instinctually at this point that water is a bent molecule. But why? Why is water crooked? Unbonded atoms within a molecule generally like to be as far away from each other as possible, especially if they have the same partial charge as the two hydrogens do with their partial positives. But something is keeping those hydrogens closer together than they would like to be. So why on earth are they not stretched out as far away from each other as possible? I ask this because if they were, the water molecule wouldn't be polar, and if water was suddenly nonpolar, we would all instantly die, as would all life on Earth. And suddenly we realized that this seemingly normal thing that we all knew about the world is really weird. And weird stuff is my favorite stuff because it means interesting questions. Interesting questions I want to know the answer to.
All right, so far we've looked at two-dimensional representation of molecules. It's not the complete story. The chemical and physical properties of these things are dependent more on their three-dimensionality, on their shape.
We spend a lot of time thinking about atoms as looking like this. There's a ball, and there's a stick, and there's another ball, and another stick. It's just a bunch of balls stuck together by these little wooden bonds. Simple, pretty easy to understand, and thus, as you have probably come to expect, it is entirely incorrect. Nuclei really can be understood as little balls, and that's more or less correct. Though when you get to some of the bigger, less stable ones, they start looking more oblong and weird, like a rugby ball. Atoms are basically ball-like as well, with electrons in a spherical cloud around the nucleus. But molecules, as we discussed last time, do not look like balls on sticks. Bonds don't form into neat little lines. They form from overlapping electron clouds, or shells, flowing around the nuclei of bonded atoms. If you really get down there and understand what they look like, they're like lumpy, clumpy globs of probable electron locations. And these lumpy clumps of probable electron locations do not behave the way you might initially expect them to behave. Oh no, that would be far too simple. They behave based on quantum mechanical three-dimensional wave functions, probabilistic distributions of electrons in space. And yeah, by the end of this episode, you're gonna understand what I just said, and it's gonna be awesome.
Yes, it is.
These orbital configurations determine the shape of molecules, and the shape of molecules determines how they behave, what forms they take, what properties they have. It's pretty dang amazing, really, that wave functions determining the probable locations of electrons keep water bent and thus polar, and thus able to dissolve nutrients and form a stable home for our cells so that we can walk around as weird bags of mostly water, thinking about stuff, making YouTube videos, trying to learn more about the world, or maybe just trying to pass a test.
All right, here we go. So what is the 3D shape for water? It is going to look kind of, if you use your imagination, like this. The angle here is 104.5 degrees. we're not to any numbers yet. This is just, I'm still setting the stage. That angle, what we call bond angle, is the angle between pairs of electrons. This one right here, that is the bond angle. That is the bond angle. The molecular structure or the geometric structures are determined by focusing on the pairs of electrons that are around the central atom. Basically, if you can count to 6, you should be able to get this right. If you can count to 6, you should be able to get this right. What is the VSEPR model? It is a model used by chemists to predict the shape of molecules. What does it stand for? Valence, shell, electron, pair, repulsion. What's wrong? Keep in mind, I don't print these off. Okay, so valence shell just means outer shell. So it's those top 8 electrons. The electron pair, as we've already seen, they come in pairs, don't they? Repulsion model. Okay? Ever met somebody that you're repulsed by them? You just want to get, you cannot wait to get away from them. Well, this model kind of makes sense, and then it kind of doesn't. Okay, what makes sense? Well, electrons are negative, and they don't like other electrons. So they'll want to get away from each other. Okay? What does make sense? What does not make sense? Well, why are these electrons who don't like each other in pairs? Why are they in pairs? All right, so let's look at the third of what I call the tetrahedral family, because they're all the same basic design, but their names are a little different. And for this one, of course, we have our favorite, water. All right, who would like to draw the dot diagram, or at least describe the dot diagram for water? Thank you, Malachi. Hydrogen, how many? Well, maybe a total of 2, but how many each? What column is it in? Okay, so 1 times 2 plus oxygen. Equals, so we have 8 electrons to place. Ready? Can you count to 8 by 2s? Let's go. And of course, we don't put any dots around the hydrogen. Can anyone tell me why? Kanan? Yes, hydrogen is completely satisfied with 1 pair. Okay, but now that we've been enlightened, we know that this is wrong, isn't it? Okay, these guys are going to push against each other so that we end up with something that looks like this. Okay, and it's still, can you see that it's still the same shape? Oxygen, dot, dot, hydrogen, hydrogen, dot, dot. See that? Now, the reason why it's called bent is that when you're naming it, you disregard the ghosts. So that looks like a line that has been bent. A line that has been bent. Any questions? Okay. Next. And I do have some models. Sometimes it's much better to actually feel these things and touch them. So this is 4 sides, but all the sides are bonded. So this is what? Tetrahedron. This has 4 sides, but only 3 of the sides are bonded. So it's pyramidal. This one is still 4 sides, but only 2 sides. So it looks like it's been kind of bent. So pass those around. Please don't take them apart and rearrange them. That drives me insane. All right, here we go. BCl3. Actually, let's not do that because that one's a little confusing in that it is an exception to the rule. How about NO3 minus 1? It's a little harder because it is a polyatomic ion, but I think somebody here can handle it. So, volunteer. Thank you, Jasmine. Nitrogen, how many? Oxygen, how many? Times. And what does the minus 1 mean? Do we take away 1 or do we add an extra electron? All right, so what is 5 plus 18 plus 1? Who's in the middle? Okay. And can you count by 2s? Let's try it. Okay. So we've now placed all our electrons. Does everyone have 8? Because 8 is great. Jasmine, does everyone have 8? Ooh, who does not have 8? Okay, so when you have used up all your electrons and somebody still is not happy, what are you allowed to do, Jasmine? Double up. So which one do you want to double up? Okay, so that means when you double up, you remove a pair that's not being used, and you create a double bond. Okay, we're technically not done. How do we communicate to somebody that this is an unusual situation where you have extra electrons? Jasmine, how do you communicate with somebody that this is an unusual? Brackets and the charge. So what is the brackets and the charge? What is the charge? -1. All right, now that we understand the VSEPR model, we understand that this is wrong because these 3 things, and even though it is a double bond, consider it a side. These 3 sides need to get as far away from each other as they possibly can. So right now, one of them has an angle of 180 and the other 2 have angles of 90. Is that the best we can do? No. From geometry, we know that they can all have an angle of Well, you all stink in geometry. What? 120. So that is correct now. You all agree? 120? Okay, that is called triangle in a plane. Trigonal planar. And it looks like this. So if you have three sides, what is the shape? Trigonal planar. But some of you are sitting there going, Ms. Rhea, that doesn't have three sides, it has four bonds. Okay, remember, I've already told you this. A double or even a triple bond, because they're taking up the same location, is still considered one side. So yes, this only has three sides. Three sides. Elaine, here's the nitrate. Pass it around. Any questions on trigonal planar?
But s&p orbitals can hybridize in other ways as well. How, for example, could you imagine sp3 orbitals forming a double bond? You can't have two orbitals mashing together in the same space, and sp3 orbitals are pretty much stuck in their tetrahedral structure. Well, if a molecule is going to be at its lowest energy state by forming a double bond, it has a nice simple solution. It only hybridizes two p orbitals with the s orbital, forming three sp2 hybridized orbitals with an unhybridized p orbital sticking up from the center. Tie the balloons together like that, and you get what we call a trigonal plane. Each sp2 orbital is 120 degrees away from the other, drawing a line straight through their centers, and you get an equilateral triangle. One of the two bonds in the double bond has sp2 orbitals merging together nicely in line with the nuclei. This straightforward sort of bond is called a sigma bond. A second and weirder bond forms, this one from the unhybridized p orbital sticking out above and below the nucleus. These atoms merge to form a pi bond. That's your nice symmetrical double bond that you see in molecules like ethylene.
Okay. So, trigonal planar. Trigonal planar. All right. Oops. CO2. CO2. I need a volunteer. Keenan. Carbon, how many? Oxygen, how many? Times? Who's in the middle? Can you count by twos? Let's try. Done. Everyone happy with 8? What are you allowed to do if somebody's not happy with 8? Okay. Yep. So, how many sides does carbon dioxide have? 2. 2 sides. And how far away can those 2 sides get? So this is a case where the 2D drawing is correct, and the thing looks to us like a line. So it is called linear. Ah, here it is. Catch, linear. Good. Try again. Catch, linear. Good catch. Better catch. Behold, linear. And then things get really interesting. But before then, let's practice. NH4 positive, volunteer. Thank you, Reagan. Nitrogen, how many? Hydrogen times, we're not going to worry about angling it or dipoling it. Just draw it and shape it. Does that say draw it, shape it? Okay, kill, hybridize, angle, and dipole it. It's more for honors chemistry type stuff. All right, and what does the +1 mean? We've encountered minuses. What do you think the +1 means? Yeah. So what is 5 + 4 - 1? All right. Who's in the middle? Can you count by twos? Here we go, because you're going to be on video. 2. Okay, so this is an unusual situation where you had to take away an electron. How do you communicate to somebody reading this that this is not what it seems? This is an unusual situation. That's right. Put the brackets. And if you have a bracket, then I'm going to say to you, oh, so it's an ion. Did it lose or gain electrons? And you would have to tell me that. What is it? Okay, so what do we call lost one? How do we write that? And the charge is? Okay. To shape it, all you have to do is look at what's around it. You ready? 4 bonds around it. Any ghosts? No. So what is 4 bonds called? Look at your notes. 4 bonds called? What if it was 3 bonds and a ghost? Pyramidal. What if it was 2 bonds and 2 ghosts? What if it was 3 bonds? And what if it was only 2 bonds? All right, volunteer. Thank you, Sierra. You raised your hand. Well, that's too bad. You raised your hand. Go, Sierra. Very good. Fluorine times is good. Who's in the middle? Can you count by twos? Here we go. Everyone happy with 8? Who's not happy? Let's see. Count. No, nitrogen's good. Okay, so everyone's happy with 8. All right, Sierra, what shape will it be if it has 3 bonds and a ghost? Look at your notes. Very good. How about this one? Volunteer. Anybody else want to stretch so I can volunteer you? Thank you, Bobby. You metaphorically stretched. Hydrogen, how many? Sulfur? Well, I'm asking for the outer shell electrons. So hydrogen, how many outer shell electrons? So 2 times 1 is 2. That's what I thought. That's why I thought you said 2. And sulfur? 6 plus 2 is excellent. Who's in the middle? Can you count by twos? Let's try it. Okay, you're going to want to put electrons around the hydrogen, but that would be a bad mistake. Why? Okay, so we're going to have to now work inward. Is everyone happy with 8? Except for hydrogen, who's happy with 2? Okay, what shape has 2 bonds and 2 ghosts? Any questions so far? Cassidy! Thank you for volunteering. Chlorine, how many? Oxygen, how many? Times? And what does the -1 mean? Very nice. So 6 times 3 is? Plus 8 more? Very nice. Who do you want in the middle? Can you count by twos? We'll see. Go. Everyone have 8? Okay, so this was an unusual situation where you had to add an electron. How do we communicate that to somebody? Nice. Okay, so what is it if it has 3 bonds and a ghost? Very nice. Now, let me introduce you to beryllium because beryllium is really, really weird. Beryllium is a weirdo that is happy with just 4. Just remember that. Beryllium is a weirdo that is happy with just 4, and I would warn you about these. I don't expect you to memorize the weirdos. Ryan, thank you for looking at me because through your eyes, I was able to ascertain that you wanted to do this one since it's weird. I guess you can relate, right? Yeah. All right, beryllium, how many? Fluorine, how many? Times? Equals? 16. Okay, who's in the middle? Can you count by twos? Yep. We shall see. 2, 4, 6, 8, 10, 12, 14, 16. Done. Does everyone have 8? No. But beryllium doesn't need 8. Okay, how many sides? And what shape does it have if it has only 2 sides? Linear, or what some people like to call linear. Line R. I guess it could be line R. Linear. Yes. How do multiple bonds affect molecular shapes? Treat a multiple bond like if it was just one pair of electrons. Treat a multiple bond as if it was one pair of electrons. Okay, so after doing these, I think we're not hybridizing or angling it. After doing these, I think I'm going to set you guys free to work on your homework. All right. Robert, thank you for volunteering. You know what you did to volunteer? Nothing. I just volunteered you. All right. C, how many? Oxygen times. What does the -2 mean? You guys beginning to see this, understand this? You know, it follows definite rules. It's not as, I mean, honors, it's trickier in honors. But for you guys, this is just, I want you to follow the rules. All right, total. Who's in the middle? So continue. You know, Robert is slow, so he's giving you plenty of time. Why don't you do it on your own? Because here in a second, you are going to be doing it on your own. Then you compare to Robert because he is turtle-like, but he always gets there, isn't he? He always gets there. All right, who's in the middle? Can you count by twos? All right, let's see. Done. All the electrons are placed. Is everyone happy with 8? So if somebody's not happy with 8, what are you allowed to do? Who do you want to double bond? Now are we done? No, because this is an unusual situation where I gave you 2 extra electrons to play with. You realize without those 2 extra electrons, you could not have made this work. So this is an unusual, how do you communicate to people like Danielle that this is an unusual situation? Okay, then Danielle will look at you and go, well, did you lose or gain electrons? And what is the charge? Okay, so what shape is it if you have 3 bonds? Why don't you look down in your notes? Most people would call it trigonal planar, but if you want to call it triangular planar and add all those vowels in there, I guess that's fine. All right, Danielle, thank you. Nitrogen, how many? Times? 3. And what does the -1 give you? All right, so who do you want in the middle? Ready to count? Yeah. Go. 2, 4, 6, 8, 12, 14, 15, 20. Done. Is everyone happy? No. So what do you do? Double bond. Who do you want to double bond? Why the right? What is wrong with you people? Why everyone wants to do the right? What's wrong with the top? What's wrong with the left? Fine. Right. Are you done? No. What? Now are you done? Yeah. Actually, no, because I gave you an extra electron to play with. Okay, so what is this if you have 3 bonds around the middle? You can pronounce it like that if you wish, but most people would pronounce it trigonal planar. Trigonal planar. But hey, you know, you can pronounce it however you want to pronounce it as long as you spell it correctly. So it's EP, not toilet paper. Letter C, you know, we just did that a little while ago, so I think you can probably remember letter C. So you now should be able to do the homework. Let me give you the homework.